Hello everyone, I'm Moscoso Thompson, and in this presentation I will summarize the results of our SHREC 2020 track on retrieval of digital surfaces with similar geometric reliefs. This contest was organized thanks to a collaboration between the CNR Imati and the University of Verona, both in Italy. In addition, this work was possible thanks to all the participants in this contest. You can see all the names and affiliation of the participant in this slide. This contest focuses on the characterization of geometric relief, which are small and repeated features on the surface of 3D models. They are an important characteristic of a model and they are independent from the overall shape, meaning that two objects may represent different shapes and be characterized by the same relief at the same times. Of course, the vice versa is also true. Geometric reliefs are key for many applications, such as the analysis of ornamental decoration, material detection, and other similar tasks. You can see examples of models that are characterized by different relief at the bottom of this slide. The goal of this contest is to create a benchmark to evaluate the performances of the methods that assess local similarity between two objects based on geometric reliefs. In short, the relief retrieval task. The relief retrieval works as follows. Starting from a dataset and a model Q of that dataset, the task consists in assessing a distance between Q and all the other models of the dataset based only on the relief on the surface of the model, so not based on the shape of the model and other properties. Eventually, this will give us a distance or a dissimilarity evaluation between every couple of models of our dataset, perfectly represented by a distance matrix or a dissimilarity matrix. We created a new dataset of models characterized by reliefs. In particular, our dataset has 220 models characterized by one of 11 different reliefs. For the dataset creation, we started from 20 base models. These models in particular can be trivially flattened and they have a non-trivial topology. Relief classes are generated starting from freely available texture that you can find on the internet that are converted into binary or non-binary height maps. Such height maps then are projected on the base models, possibly uncorrected on the more complex geometry, such as handles or other protrusions. This is done for all the relief classes applied on all the base models. You can see an example of the final results we obtained after this process in the right part of this slide. A total of 8 methods are proposed for this contest, 2 by the same group. Most of the methods come with more than one run, characterized by different settings. We have a satisfying variety in terms of strategies used to face the problem, and for the first time in this kind of contest, we received some methods based on machine learning approaches with very different performances. In the following section, we are going to describe the methods proposed by the participants. As a premise, most of the methods are complex and very hard to summarize well while staying in the time limits for this presentation. For a more in-depth description of our methods, please check the paper you will find in the proceedings. I will try now to give you a few words for each method in order to describe the general idea behind it. I thank you in advance for your patience. The method augmented point pair feature descriptor is a 3D object descriptor made of local features, mainly angular variation. Such local features capture the geometric characteristics and properties of a set of surface patches, each centered at a point which incorporates the geometrical relation between points and their nearest neighbors. Such characteristics, sampled on a number of key points, are the data on which a Gaussian mixture model is trained using diagonal covariances. Then a global Fisher vector is computed relying on the Gaussian mixture model. Finally, the distance between two Fisher vectors is computed using the cosine metric you can see at the bottom of the slide. This group submitted 2 methods. The first is the deep feature ensemble. First, in a pre-processing step, models are oriented so they stand vertically, and this is done by looking at the eigenvector of all the vertices. Then, multiple images from different points of view are sampled from the model, and the one with the most relief is considered. This is done by considering the Sobol filter to compute the gradient on the images. Finally, the largest square image inscribed in a model is extracted and is considered as the representative of that model. For these methods, authors used multiple pre-trained networks such as the ResNet, DenseNet, and VGG. Authors considered intermediate layers of these nets and concatenate them in one final feature vector. Finally, with the help of the average query expansion, a dissimilarity matrix is computed based on these feature vectors. This method, called orientation histogram, shares the preprocessing step with the previous method. Starting from the largest square representation, the gradient of the images are computed using the Sobel filter. From the latter, model and angle are extracted for each point. Angles are placed in an histogram weighted by the value of the models. Such weights are distributed also on the two nearest neighborhoods of the vertices. Then, histograms are normalized. Finally, again with the help of the average query expansion, a dissimilarity matrix is computed based on the distance between the histograms. This method is called deep patch metric learning, and it works in two main steps. The first one involves the extraction of patch images from the mesh surface to correlate information about relief from the global shape of the mesh. This is done by sampling randomly the surface and by considering the flattest neighborhood of the sampled points. Such neighborhoods are then converted into images. In the second step, authors used these images to train a Siamese neural network to learn the distance function between each pair of images. In particular, authors used VGG16 without fully connected layers. Finally, a distance delta between two objects is defined as the minimum distance between any couple of images belonging to the two surfaces with the help of the similarity function learned by the Siamese network. These methods consist of computing the distance between two shapes using the signature quadric from distance. First, multiple patches are sampled from the models and converted into point cloud. Then, such point clouds are given to a pre-trained PointNet neural network. Authors, in particular, used the ModelNet 10. The 1024-dimensional feature vector obtained by the PointNet is then used for the classification. Eventually, its shape in the dataset is represented by a number of descriptors, which are used for computing the signatures, and eventually such signatures are compared using the SQFD method. This method sets a set of parameters, such as the radii of the patches and the number of patches per model. You can find a more detailed discussion for this kind of parameters for this method on the paper. This method is called smooth rugged normal angle. First, the model is smoothed with the Laplacian smoothing. Then, the angle between the normals of the smoothed and original models are computed. Such angles are used to compute the saliency of the models, which is used to perform a surface segmentation. Points with low saliency are considered to lie on flat areas, while high saliency means that the points lie on a texture. The computed segmentation leads to the creation of two histograms for the angles, one for a flat area and one for a textured area. These histograms are then weighted, concatenated, and are used to compute the final distance matrix. This method is an application of the well-known mesh local binary pattern, and it works in 4 steps. First, up to 6 patches are extracted from the object surface, obtained by intersecting the mesh surface with the free eigenvector of the covariance matrix centered at the center of the mass of the object. Then, the tessellation of the mesh is regularized by projection. After this operation, the ORF descriptor is computed. This operator allows for the computation of convolution-like operation locally and directly on the mesh. Finally, the dissimilarity metric based on the descriptor applied is computed. Authors submitted a run for each of the following operators: mesh LBP Sobel filter, mesh LBP sharpen filtered, and a standard LBP without filters. This method is based on using the KD3 fast library for approximate nearest neighborhood to match the query to other objects in the database. The FLAN is a method that is used for evaluating the correspondence between two objects by finding the distance between the extracted features. This method works essentially in 2 steps. First, a preprocessing steps that only extract the surface information. Then, the application of the KD3 FLAN method on such information. Multiple patches are randomly sampled on the mesh, and then the ones with the lower mean curvature and the highest mean variance of normal are considered. For each patch, the authors detect key points that are suitable for effective descriptor and matching. Then, the local feature descriptor on shot 352 is applied for each of the detected key points. The
Obtained features are then matched using the KD3 flank correspondent matching method, and such information are used to create a dissimilarity matrix. If between two models no matches are found, then the value in the dissimilarity matrix is set to 1. In the following, I will show you how these methods perform on our dataset. This will be done with different evaluation measures. Here you can see an overview of the performances for this contest. We used different evaluation measures, and each one of them suggested us something about the methods, on how well or bad they perform on this dataset. Let's now focus on some of these evaluation measures individually, so we can draw the conclusion for our contest. Here, for example, you have all the numerical evaluation used in this contest, like the nearest neighborhood evaluation, the tier evaluation, the MIP value, the measure, etc. In order to have a quick grasp on the table, please notice that the values near 0 are in red, the value close to 1 are in green, with all the gradient between these two colors. At first glance, you can see that there are some methods that perform really well, or just well, and just a couple of methods that seem to have issues with this task. Please also notice that both methods with or without machine learning approaches or components can perform decently, or really well. Still, the best performing method in this table, that is the DFT, belong to the first kind of methods, or rather the one with the machine learning component, in particular transfer learning. It's worth notice that methods that use transfer learning in general have results that are more stable from when comparing the nearest neighbor evaluation and the first and second tier evaluation. This highlights the robustness of these methods and approaches that, despite having more room for error in the first and second tier evaluation, still can correctly identify the similarity across the model based on geometric reliefs. For this contest, we also consider both precision recall curves and ROC curves as evaluation measure. But eventually both were saying the same thing. So here we are just reporting the ROC curves of all the runs of the methods. Please remember that a diagonal line in this kind of plots correspond to a random retrieval. One of the things that we can observe from here, but also from the previous table, is that the different runs of a method that change just some parameters don't really change the final performance of the method by that much. Of course, this doesn't happen for methods that change an entire component across the different runs, such as the mesh LVP that change filter from run to run. These evaluations take a closer look at the performances per class. In particular, confusion matrices are a visual representation of the nearest neighborhood for each class. Similarly, tier images are a visual representation of the nearest neighborhood in black, first tier in red, and second tier in blue for each model. You can check these images more clearly in our paper. Still, we can draw some conclusion. First, either for good performing or bad performing methods, you can see that there is no class particularly harder or simpler than the other. This means that the generalization of the concept of relief for the proposed methods was robust enough for this contest. Moreover, you can observe that the methods that convert the models into point clouds or that are based on CNN trained on point clouds seems to be suboptimal for this task. Our final thoughts on this contest are the following. First, we saw great interest in this task based on the number of runs submitted and the number of participants. Moreover, we saw a satisfactory variety of approaches to the problem, most of them with good performances. Moreover, in the previous years, my co-authors and I organized other contests based on the relief retrieval task, and this is the first year in which participants proposed methods with machine learning approaches. For the future, it could be interesting to be able to create bigger and more complex datasets that can better fit this kind of methods. Talking about new contests, the performances of some of the methods we received this year suggested us that it could be possible for next year to create a contest on a harder version of the relief retrieval problem, which is the relief or pattern recognition. In this, surfaces are characterized by no pattern, one pattern, or more than one pattern. The goal is starting from a set of query relief and another set of models to check if and where the query reliefs are on the model of a given dataset. And that's it. If you have any question, you can ask me now in the live Q&A section, or you can also reach me at the email address you can find in this slide. Thank you again for your attention.